Okay, so right now we're going to go over the 5 facts of climate change. And so the basic questions we're going to answer here going to address what are greenhouse gases and the greenhouse effect, what impact the humans have on the climate, what are causes and consequences of climate change, do most scientists agree that humans are impacting the climate, and also kind of at the end, what if we are wrong about climate change. Um, so when you think of climate change in the United States, it's a controversial topic. It's become very political, and what I want you to understand is this is pretty unique to the United States, and most industrialized countries, and even ones that are industrializing. You look at, European countries, even over to China, India, most countries in the world believe that climate change is a really important problem that we need to solve. And the debate is more, what do we do about it? In the US, it's become very controversial because it's become political. And it's become political because there are moneyed interests, so corporations that make a lot of money from things that are known to be contributing to climate change, that are influencing politicians to speak, indicate, basically muddy the waters to make people believe that climate change is more controversial than it is. Now, to be clear, we are not 100% certain on all the aspects of the science. That's one of the main reasons why I'm going to go over this today. I'm going to present to you the 5 facts of climate change. I'm going to tell you what we know, some of the things that we don't know. But I want to be very clear that this is, among scientists, this is not a controversial topic. It's only among politicians, and the politicians themselves are only that way because they are influenced by people and corporations and so forth that have an interest in people not believing in climate change. So just to keep in mind, this shouldn't be that controversial a topic. Or really, we're arguing about the wrong things. Really, what we should be arguing about is what do we do about it, not is the science true. Okay, so let's go over a few important terms here. First of all, some important terminology. Hopefully you've seen a lot of these before. The greenhouse effect, the first one here, the greenhouse effect is this term that's used to describe this phenomenon whereby basically there are gases in the atmosphere that keep the Earth warmer than it would otherwise be. Now keep in mind, this is not just specific to the Earth. There are other planets that have an atmosphere that does this, Venus primary among them. So it's just a general, this is just physics, the physics of certain gases in the atmosphere that keep the surface warmer than it would otherwise be, and the lower atmosphere warmer than it would otherwise be. And we'll go over those details. So that's the greenhouse effect. It's just something that happens. It's happened before humans were around. The enhanced greenhouse effect is the additional greenhouse effect that things that humans have been doing, namely adding greenhouse gases to the atmosphere, have increased the greenhouse effect. Okay, so human impact on the greenhouse effect, that's your enhanced greenhouse effect. Okay, so the greenhouse effect itself, natural, normal, it happens. It's happened for hundreds of millions of years, billions of years even before humans were around. The enhanced is the one that we kind of have a little bit of control over. So greenhouse gas is just a gas that absorbs infrared radiation, contributes to the greenhouse effect. We'll talk about this in a minute. Anthropogenic, big fancy college word here. Anthropogenic really just means caused by humans. If you think of the break down the roots here, you have anthro, you think of anthropology, right? It's the study of humans. So anything that's anthro is humans. Genic, you think Genesis, creation, right? So anthropogenic is just a fancy way of saying it's caused by humans. It doesn't refer only to climate change. You can have anthropogenic species loss, anthropogenic water use, whatever. Anything that's caused by humans is anthropogenic. And kind of putting these two together, anthropogenic climate change is the component of climate change that is believed to be caused by humans. Sorry for the typo there. So this is sometimes referred to as HEW or anthropogenic climate change, normally just climate change. Okay, so that's kind of setting a little bit of a foundation with some terminology. So let's start with our 5 facts. All right, so fact number 1. We know that greenhouse gases trap heat in the atmosphere. This is not under dispute. We've been knowing this for a long time. Any even half-serious scientist knows that this is a fact. I'm sure you could find some weird little dark corner of the internet that says that this is not true, but this is settled science. We also know that without the greenhouse effect, life on Earth, as we know it, would not be possible. So how does the greenhouse effect work? All right, so I'm going to show a short video here. Fair warning, this video is, as you'll see, is very old. I have watched, I can't even imagine how many videos to try to find one that succinctly describes the greenhouse effect. This is actually the best one. For any of you that are, hold on a second, old enough to remember someone popping in a VCR tape, this is what it felt like. So this is, imagine me virtually popping in a VCR tape here. Oops, sorry.
Earth's greenhouse effect greatly affects climate. See if you can describe how carbon dioxide and water vapor cause the Earth's greenhouse effect. Also, see if you can describe how the greenhouse effect maintains the surface temperature of Earth. Scientists have long known that the presence of an atmosphere keeps the surface of the planet warmer than it would be without an atmosphere. In fact, without an atmosphere, the surface of the Earth would be about 30 degrees Celsius cooler than it is now. In order to understand why, we need to consider the surface of the Earth and its atmosphere separately. Because there is a radiative equilibrium, we know that the planet emits enough long-wave radiation into space to equal the solar radiation absorbed by it. However, most of the long-wave radiation that is emitted by the planet into space is emitted by the atmosphere rather than the surface of the Earth beneath it. Although the surface of the Earth does emit long-wave radiation, only about 10% of this radiation passes through the atmosphere and escapes into space. The rest is absorbed by clouds and by greenhouse gases in the atmosphere. There are many greenhouse gases, but the most abundant greenhouse gases are water vapor and carbon dioxide. Short-wave radiation from the sun passes through greenhouse gases, but long-wave radiation is absorbed by them. Greenhouse gases absorb long-wave radiation that is emitted by the surface of the Earth. Subsequently, they re-emit the energy as long-wave radiation in all directions. About half of the re-emitted long-wave radiation does escape into space and contributes to the planet's radiative equilibrium. About half of the long-wave radiation emitted by the gases is directed back toward the surface of the Earth. As a result, a continual exchange of long-wave radiation takes place between the surface of the Earth and the atmosphere above it. The long-wave radiation contained in this exchange causes the warming effect known as the greenhouse effect. This phenomena is known as the greenhouse effect because, like the glass in a greenhouse, the atmosphere traps some of the energy beneath it. The greenhouse effect produces a warmer climate on Earth than would be possible without an atmosphere. In summary, water vapor and carbon dioxide allow solar energy to penetrate Earth's atmosphere but prevent much of the long-wave radiation emitted by the surface of the Earth from escaping to space. This trapping of long-wave energy is called the greenhouse effect and enhances the surface temperature of the Earth.
Okay, so again, really good description there. Despite the obvious age of the video. So let's readjust here. Okay, so just to summarize here, we have these gases in the atmosphere, including greenhouse gases. The sun emits almost entirely shortwave radiation. Okay, so shortwave radiation passes right through greenhouse gases. They're basically invisible to the shortwave radiation. If sunlight is reflected, the sunlight bounces back out. It's still shortwave radiation, so it'll pass right back through those greenhouse gases, does not get absorbed. However, if the sunlight's absorbed by anything on or near the surface, if you walk outside today and it's sunny, you're absorbing shortwave radiation from the sun. Doesn't matter if it's winter, summer, spring, or fall. That sunlight actually heats up your skin or your clothes or whatever, and then that energy that's re-radiated, okay, that is what's called long wave radiation, okay? And so anything that re-radiates, unless it's a really, really high temperature like a light bulb, something like that, it's going to emit mostly long wave radiation. Now here's the key. Whoops, sorry. Greenhouse gases in the atmosphere absorb long wave radiation, but not short wave. So that's how the greenhouse effect works. Sunlight passes through. If it's absorbed, re-radiated, then the greenhouse gases can absorb it, and then it'll re-radiate it actually in all directions, but about just law of averages, about half of it goes back toward the surface. And that's how it keeps it warmer. All right? So in summary, the sun emits mostly shortwave. Greenhouse gases do not absorb shortwave. If shortwave is reflected, it will go back out into space. If it's absorbed, if shortwave is absorbed, it's re-emitted as long-wave radiation, and the greenhouse gases absorb and re-emit about 50% of the long wave back towards the surface of the Earth. That's it. This is not controversial. Scientists know this. They've known this for almost 100 years. I mean, it was theorized over 100 years ago. This is not controversial. Okay, and so that's fact number one. All right, so fact number two is that we know that humans are causing concentration of greenhouse gases to increase, and we know also that the number one anthropogenic source, remember, caused by humans, of greenhouse gases is energy use. All right, so the greenhouse gases, we have carbon dioxide, methane, nitrogen oxide, water vapor, CFCs. The two that we are primarily worried about are carbon dioxide and methane, and really the big one is carbon dioxide, okay? So this shows you for the last about 2,000 years concentrations of this line. Your red is CO2, here's your nitrous oxide, and here's your methane or CH4. So you can see right around this period of time, you can see right around the early 1800s, the concentrations of all of these in the atmosphere spiked. And what happened there, it was the Industrial Revolution. We started using more fossil fuels, and we talked about this a little bit earlier. Okay, right around 1800, through the 1800s, and then just shooting up ever since then. Okay, so this is a chart of concentration. Concentration just means the amount in the atmosphere. Okay, so higher concentration means more of that gas in the atmosphere. The second thing that's important to note here is that greenhouse gases in the atmosphere, they are dispersed evenly globally. So the United States and China are the two biggest emitters in the world, for example. For all intents and purposes, there's no more CO2 above the United States and China than there is anywhere else. So once you emit CO2, so like I drove to work today in my car, that CO2 that I emitted out of my tailpipe, that just mixes with all the gases in the atmosphere. It's not, it's not considered as an increase in the United States concentrations. It's global, okay? So everything's global because it impacts everybody globally. So that's also important to remember as well. Just some other minor point. Now I'm not going to go over this in detail. This is just an FYI. So we usually measure in parts per million. Carbon dioxide is measured in parts per million. Global warming potential. So I don't want to get into these details, but if you're interested, you can look up global warming potential. Basically, all this means is that methane and nitrous oxides are much more powerful in terms of the warming impact than carbon dioxide. So carbon dioxide is much less potent than methane or nitrous oxide. However, the one you hear the most about it is CO2. And so the question is why, if these are much more potent, why are we worried so much about CO2? The main reason is that if you look at the greenhouse gas emissions, so this is the U.S. greenhouse gas emissions, and these are global greenhouse gas emissions, you notice carbon dioxide is about 80%. 80% of the impact that we have on the climate, of the impact that we believe we have on the climate, is from carbon dioxide in the U.S. And globally, it's right around 80% as well. Okay, so you can see methane is important, but not as nearly as important as carbon dioxide. So that's the main reason we're worried so much about CO2. It's also the one that we happen to know it's relatively easy to control in that we know exactly where it comes from. Okay, so just some evidence that CO2 emissions are increasing. This is a chart of the actual measured carbon dioxide concentrations since 1958. So we've been directly measuring them since 1958. So we started out in 58 around 315 parts per million, and we're as of October of 2017, and this has increased since then. You can see a clear trend up, right? So this is not a proxy. We're not sort of saying, well, we know the tree rings and ice cores analysis. This is directly pulling gas from the atmosphere and measuring the exact concentration. We know this for an absolute fact since 1958, increasing. Just an FYI, you notice this a very distinct pattern. It goes up and it goes down. This happens, goes peaks and and then a valley once a year each. All this indicates, or this is evidence of, in the northern hemisphere when we have our summer, the CO2 concentration drops because most of the land mass in the world is in the northern hemisphere. And so as the summer peaks, there's more vegetation that grows that's pulling CO2 from the atmosphere. So it actually drops, a good like 5 parts per million in the summer, but then it goes back up in our winter in the northern hemisphere. Speaking from the northern hemisphere. So northern hemisphere winter it spikes because vegetation dies. Northern hemisphere summer it drops because of all the vegetation growing. Okay, so the point here is that concentrations have been going up in terms of exact measurements since 1958. If you look since about 400,000 years ago, so here's your CO2 concentrations. You notice there are rises and falls, but we are currently well above any level of CO2 that's been seen for 400,000 years. Okay, so this was 400,000 years. If you look at 800,000 years, the last 800,000, we've never really been above 300 parts per million. Again, we're up at 403 parts per million. So the human impact on the climate or human impact on emissions is very, very clear. This is us. This is from burning fossil fuels. Okay. Again, this is really not controversial at all. If you look at also the relationship between carbon dioxide and temperature, now this is a little harder to verify, but you look. So here's your the pink line is your temperature, and the blue line is your carbon dioxide concentration. You can see it follows very closely. So again, it's just more evidence that there is a connection between CO2 and the climate. Okay, so something that's important to point out is that the natural emissions of CO2. So the Earth is constantly cycling carbon dioxide in and out of the atmosphere. So we have something called the carbon cycle. You probably have heard about this at some point in your academic career. So we know that trees pull in CO2 and then they die, then they release it. Believe it or not, the oceans are actually the biggest absorber of CO2 in the world. So the oceans absorb, millions of tons or billions of tons, excuse me, of CO2, and then they emit it back out. The soil actually absorbs CO2 and emits it back out. And then there's our contribution with fossil fuels and land use change and so forth. So the point is that the Earth naturally cycles carbon dioxide in and out of the atmosphere all the time, to the point that about 770 billion tons of carbon dioxide are emitted by the Earth naturally each year. Humans add around 30 billion tons, so 700 to 800 billion tons versus 30 billion tons. Now these numbers, they're approximate, but these are from, this is from a good source. So you think about it, the Earth naturally emits like 30 to 40 times more CO2 than humans add. So why are we so worried about human emissions? And so the reason that we care, even though humans add a relatively measly amount, is that we're basically throwing the carbon cycle out of balance. Okay, and so if we weren't around, there's a good chance, at least right now, that CO2 levels would remain constant. Okay, so we're just throwing the whole system out of whack. So that's why the anthropogenic emissions are so important. Okay, so if we look at where the emissions are coming from, so here's U.S. carbon dioxide emissions by source. So we have electricity, which is fossil fuels, transportation, that's our oil, mostly fossil fuels, industry, that's fossil fuels, residential, commercial, that's like heating and cooling, that's fossil fuels. So the bottom line here is that basically all of our CO2 emissions come from fossil fuels. And so the single best way to reduce emissions is to reduce fossil fuel use. Again, this is not controversial. We know that when you burn a fossil fuel, it emits CO2. And so we know that if we really want to reduce our emissions, that's easily the single best way to reduce our emissions. Okay? All right. So now we have our two facts. Let's go to fact number 3. So fact number 3 is that the climate is warming, oceans are rising, Arctic sea ice is melting. So if you look at the climate, the trend over time, we've been doing direct temperature measurements globally since 1880. So this chart shows you the anomaly. So that means, is it colder or warmer than normal? Okay, so what it does is this chart takes all of these temperature readings, okay, over the last 130 plus years, and it finds the average of them. These are global temperatures, okay? So basically this line is the global temperature average over the past 130 or so years. And then these lines show you whether it was colder or warmer relative to that line at the time. So you can see obvious trend. It's, there's peaks and valleys. Obvious trend overall is that the climate has been warming over the past 130 so years. Again, these are just different climate models. Okay. This is a recent video. I'll show you this. This is a short one. Sorry, let me try that again. So there's nobody talks in this one. So this map is showing you the temperature anomalies since the late 1800s. Blue is colder, yellow and red is warmer. And this is from NASA, so it's a really good source. So now we're in the 1990s. So yeah, pretty dramatic. That's just one illustration of how the climate has gotten warmer over time. So again, this is really not controversial. We know that this is what's happening. Okay. This is another chart. Feel free to click on this on the PDF, but this is another display of temperature anomalies through time. Okay, so here's a chart again from NASA. And this is the 10 hottest years ever recorded, excuse me, NOAA, which is another good source. This is the 10 hottest years, or these are the 10 hottest years ever recorded. So take a look at this chart. We have our ranks, so from 1 to 10. This is the year, and this is how much hotter than normal it's been. So what do you notice about this chart? So feel free to press pause. So the thing that really jumps out to me, if you look at these years, right? Every single year, except for this one, 16 of the hottest 17 years, so if you would go down to actually the top 17, 16 of the hottest 17 years ever recorded, okay, in recorded human history, so since 1880, have been since the year 2000, so 2001 and on, right? And the only other one that's outside of the top 17 that's not in this the aughts in the 21st century is 1998. So it's not like it was 200 years ago. So it's clear that the climate it's warmer. I mean, now you got to be careful because we can't predict the future. I mean, you remember you saw this chart here. I mean, the temperatures do spike, they do swing, but you notice these swings, even the downward swings, are now hotter than the upward swings were in the past. Okay, so we don't know that this is going to continue, and you have to be careful about looking just at short-term trends. But it is pretty clear that it's very clear that the climate is warming, at least in the last 2 decades or so. Okay, and the long-term trend has also been very, very clear. In terms of sea ice, this is a very recent, at least from when I posted this video in early 2017. I found this interesting because this is from Fox News. Okay, so Fox News, known to support climate deniers, very generally skeptical of climate change. I mean, this was a summary on Fox News that was summarizing this research from the National Academies of Science, is a really good source, that found that sea levels have been not only rising but rising faster than we have thought they would be. So again, this is not controversial. The sea levels are rising, and it's due to both expanding water as it warms up, but also melting ice. Um, and as they say, this is almost certainly a conservative estimate. So I found this pretty fascinating. This so a source like Fox News would have this report here, and it's again the evidence is really clear. I mean, this is just it's just science. It's just a fact. So there's really no controversy here. Okay, so there's our first three facts. Fact number 4 is that if climate change continues to happen, the results will almost certainly be catastrophic. I'm not getting into a whole bunch of detail here. You're welcome to look. Um, it's really easy to find information online about the probable impacts of climate change. And we have rain and flooding, droughts, crop failure, sea level rise, diseases, refugees. There's all kinds of stuff here. I don't have time to get into it all. But if you look at the overall impact, so taken as a whole, the range of published evidence indicates that the net damage costs of climate change are likely to be significant and increase over time. So what does this mean? Translation: it's bad and it's going to get worse. Okay, so again, there's a little bit of controversy here. You have some people that say, well, actually, even to take a quick backtrack here, there are some positive impacts in that longer growing seasons. For example, now you can grow, wheat and corn in southern and central Canada. So there are some minor positive impacts. So to be very clear, again, I want to stick to the facts here. There are some positive impacts when you have longer growing seasons in certain areas of the world. And some areas will be a little bit wetter, so they'll be able to, they'll be better off than they were before. But it's unequivocal that taken as a whole, okay, so if you look at global impacts, climate change will be a negative thing. Okay, so it just will be. There's going to be all kinds of issues when you just get to flooding and disease problems and crop losses and so forth. It's going to be bad. Okay, there may be some minor benefits, but overall it'll be bad. Okay, so that's fact number 4. And finally, fact number 5, there's broad scientific consensus that climate change is almost certainly being caused by humans. So I want to be very, very clear here. We don't know for a 100% fact that humans are causing the observed warming to happen. We do not know for a 100% fact. Okay? The only way we could know that is if we had our Earth, and then we had, this Earth that we're sort of experimenting on, dumping a bunch of greenhouse gases in the atmosphere, and then we had a second Earth that said, well, what happens if we don't dump gases into the atmosphere? Obviously, we can't do that, so we do the best with what we can. There's a lot of scientists that are working on this. Okay, we are so close to certain that this is the case. Okay, and you look at any real serious scientists, of the ones, and there's a couple of studies out there that show that around mid to high 90% of all the climate scientists in the world, okay, agree that the trends that we're seeing are extremely likely due to human activity. So extremely likely. So be careful here. Humans, it would be false to say that humans are absolutely impacting the climate. We don't know that for 100% fact. But that's the important thing to remember, is that doesn't mean that it's not almost certain, okay? We have a lot of theories, the theory of tectonic plates shifting. We haven't proven that, but there's no evidence against it. So here it's almost certain, and just because we aren't 100% certain doesn't mean that we shouldn't do something about it. And then you look at all these, high-level academic societies are in support of doing something about climate change because they believe humans are at fault. We have businesses all over the world, from your Microsofts to your Apples, even ExxonMobil, a major oil company, is now saying we need to do something about climate change. So the consensus is there, right? All right. So in summary, the the greenhouse effect is settled science. We know this is what happens. Okay. We know carbon dioxide is a greenhouse gas. We know that increasing CO2 concentrations and other greenhouse gases are increasing, and we know that humans are the ones that are increasing them. We know that the climate is getting warmer. We know that if climate change happens, it's going to be really bad, and we know that there's broad consensus that humans are at fault. So if you just put all these facts together, it's like we need to do something here. And there's from one of your readings, there's this physicist named David McKay, and he says, look, here's the deal. We're not 100% certain this is happening, but think about it this way. If you're riding a motorcycle at high speed and you don't have a map, but you think you're close to a cliff, wouldn't you slow down? So I want you to think about, what's the analogy here? The analogy is that even if we're not 100% certain, so let's say you're driving your motorcycle at a really high speed and you're like, I don't know, I think I might be close to the cliff, I'm not sure. Wouldn't you maybe take the precaution to sort of slow down a little bit to make sure that you don't fall off the cliff? And that's something that would be considered what's called the precautionary principle. So the precautionary principle indicates that you should try to avoid the worst case scenario. Okay, so if you think about it in terms of climate change, our worst case scenario is that we don't do anything about it and we're the ones causing it. If we're wrong and we do something about it, to this point, this is a really famous cartoon. So let's say all these scientists are completely wrong. Humans actually have no impact on the climate whatsoever. If you think about the actual impacts of what we what we know we need to do in order to address it, and we are wrong at the end of the day, at the end of the century or whatever, we cut our greenhouse gas emissions by using more renewable energy. We have cleaner water, we have cleaner air, we have more forests, et cetera, et cetera. Even if we're wrong, the overall impact of doing something about climate change is almost entirely positive. And yes, there will be some major adjustment in the economy. Yes, there will be some job loss, but there'll be more job gain. Yes, the economy will dip a little bit, but that'll come back. So if you look at the overall what's at stake, we have way more to lose than we have to gain by not doing anything. And that's kind of the bottom line. Okay, so that's it for the 5 facts of climate change, and then we'll pick up with the last little bit next.